So we have a Jared Hoberock, who's a research scientist with Nvidia, and he's going to present on building parallel algorithms with bar. So just to introduce him, Jared had joined Nvidia Research in October 2008. His interest includes parallel programming models and physically based rendering. Jared is the co-creator of the Thrust library, a high-performance parallel algorithms library. While at Nvidia, Jared has contributed to the DirectX graphics driver, Gelato, a final frame film renderer, and the OptiX, a high-performance programmable ray tracing engine. So he has received a PhD degree in computer science from the University of Illinois at Urbana-Champaign, and he's also a two-time recipient of the Nvidia Graduate Research Fellowship. So, Jared.
Thank you. All right. Good morning, everybody. So today I want to talk a bit about programming CUDA kernels and parallel algorithms in a way that's sort of nice and robust and maintainable. And this is all sort of influenced by my development work on the Thrust library, which is a CUDA library of parallel algorithms that Nvidia ships with the CUDA toolkit. And like I said, I work within Nvidia Research in the Programming Systems and Applications group, and everything I'm talking about today is open source, and it's on GitHub, so you can find it immediately. So let's get started. So here's the real title slide. So the objective of my talk is to turn you all into bulk-maniacs. So at the end of this talk, I want you to all to run home, feel very powerful programming with this library bulk. So become a bulk-maniac. So let's just dive right into it and look at what Hello World looks like in bulk. So say we've got Hulk Hogan up there. There's lots of people in this room. Say we all wanted to say hello brother to him in parallel. How would we do that? How would we write that program? So let's just look down the lines of code and see what that would look like. So if you're a C++ or a CUDA programmer, this code probably, you can probably tell just at a glance what this code does. But let's take a look inside main. So if we want to get some work started, we say bulk async. So this is like the entry point to launching all sorts of work in a bulk synchronous manner. So we say bulk async, bulk par of 1, hello. So that'll basically launch one little guy, one little bulk-maniac to say hello, brother, to Hulk Hogan here. But say, what if we wanted to get lots of work done at the same time? So say there was 32 of us and we all wanted to say hello. We take that same line, that bulk async line, and inside the bulk par, we put down a 32. So we want 32 of these little bulk-maniacs to say hello. We pass, again, the hello functor and this special token bulk root, which I'll explain a little bit later in the talk. And that will actually launch 32 of these execution agents in parallel. So what this is going to do is take this hello functor at the top of the screen here, and it's going to invoke it with this special bulk parallel group token. You can see there on the second invocation line. And this is going to call printf, hello brother from bulk-maniac, whatever. To get the index within our group, we say something like g group.thisexec.index. So throughout our talk, this is all going to become a lot more obvious exactly how this all fits together. But Hello World is easy to get going. So bulk takes inspiration from lots of different libraries. So certainly, I guess the main inspiration was Thrust. I basically wanted a really nice way to build Thrust. If you've ever looked inside the Thrust source code, it's basically unintelligible because there wasn't something like this available. So hopefully it'll get a lot better. If you're familiar at all with what's going on in the C++ standardization effort, some of these ideas should look familiar because they're basically inspiring the way that we're launching work and talking about work in parallel. Phalanx is this other library that looks very similar to bulk. It came out of Nvidia Research. So it's taken a lot of ideas from there. Cub, I don't know if you heard Dwayne talk yesterday about Cub. So Cub is Dwayne Merrill's high-performance CUDA library for building really high-performance kernels. He's got lots of examples of building really, fastest in the world sorts, fastest in the world prefix sums, and it's basically a productive library for doing for building kernels together. So it's similar in a lot of ways to what I'm talking about today. The MGPU library is Sean Baxter's modern GPU library. Basically, everything I learned about everything I know about GPU programming, I learned by reading Sean's code in modern GPU. Most of the examples I'm going to show you today in bulk have been essentially transliterated from code from that library. So it's been very influential. And of course, CUDA. The way that you think about writing programs with this library is essentially exactly the same way you actually think about writing the code, writing CUDA code. So what is bulk trying to solve? What do we actually care about? We want a good way for some definition of good to author GPU kernels. So kernels need to be maintainable, right? I need to be able to write the code, and then the maintenance process has to be tractable, right? Things can't break every compiler release, every CUDA release. Things need to be very stable. Going along with that, the code has to be absolutely robust. There can't be all these corner cases where things don't work. We want nice ways to express parallel kernels in a way that falls back gracefully. So maybe something doesn't run as fast. If some resource fails, it just gets a little bit slower. It doesn't fail entirely. The functions in the code we write, we want to be composable. And I've got some arguments that I'm going to tell you about today that basically argue that the way that we have to write CUDA code today isn't very composable because of the way that things like shared memory works. And I'm going to show you some ways to alleviate those problems to make code more composable. And productivity, basically all those three things are necessary in order to write code productively at all. We want to be able to write code that runs on the GPU in a way that's very productive, that doesn't take months and months of experimentation and twiddling to get the thing to work exactly right and exactly how we predict it to work. We want to be able to write code, in a productive way. And then finally, all this stuff has to run fast, right? We wouldn't be here talking about GPUs if we didn't care about performance. So we want to find a way to achieve those four initial goals in a way that still allows us to maintain high performance. So first I want to talk about maintainability. So when a thrust unit test fails, it's this gigantic nightmare, right? It's like WrestleMania, trying to find out what exactly happened, whose fault it is, why did this test fail, and how do we fix it? Right? So there's all these moving parts that sit beneath thrust. There's the CUDA code itself, there's NVCC, the compiler, there's the driver, then there's different GPU architectures that all work differently, all have different architectures, all have different machine constants. Who knows how they work? So when something fails within thrust, it's like, what happened? We have, it can be very difficult to figure that out. So basically, we want code that's easily testable and sort of obvious what it's doing and why it's broken. So we want things like well-defined preconditions and well-defined postconditions. We want things that can be tested very simply. And finally, I guess my test for maintainability is that if I look at some code I wrote, say, 18 months ago, I should be able to tell, at a glance what it does. That's not the case today, for various reasons when writing CUDA code, but that's sort of the goal that we want to be at, at some point in the future. Robustness. So I don't know if you've are there any CUDA programmers in the room today? I hope. Okay, good. So this talk probably makes more sense. That's good. So I don't know if you've ever written some sophisticated library code that has to launch a kernel, and you want that code to always succeed. You know that making that work takes a lot of effort because out of the box, kernels can fail for all sorts of different reasons, and the reason it fails is not always obvious. So, I'll give you some examples of rough edges that are in CUDA today. So, CUDA, what happens if you ask for too many thread blocks? Well, that's an unspecified launch error, right? What happens if your kernel parameters are too large to fit into, the tiny window of parameter memory that a CUDA kernel has? Well, that's another launch failure. What happens if the types of your kernel parameters aren't plain old data, right? They're C++ types that have weird constructors and destructors. Who knows what happens, right? Because those constructors aren't going to get called, so who knows exactly how it's going to work. If you ask for too much shared memory, that's another launch failure, right? CUDA doesn't do anything to help you there. It just tells you to go to hell. And then finally, if you don't have a GPU, you're screwed, right? Your code's not going to run. So basically, I just want a programming model that just makes it work, right? If any of these things, if I ask for too many blocks, if I ask for too much shared memory, I want things to just maybe slow down a bit. I don't want to have to actually go back in and figure out why it failed. I just, I want to make it work and make it work, fail in a way that's more graceful than just, falling over. So composability. So my big complaint with the way that CUDA works today is that the way that shared memory works forces you to write code that is not composable at all, right? So if I want to use shared memory, when I'm writing my code, I have to sort of figure out somehow exactly how much shared memory I will need in advance. And as a programmer, why should I necessarily know that, right? If I'm writing a C++ program, I don't know in advance how many times I'm going to call malloc and how many bytes I'm going to ask for malloc, right? I just call malloc, and it usually works. I want shared memory to work more like that. I want to be able to call a malloc-like function that just serves out shared memory, and if it runs out of on-chip memory, then it just sort of virtualizes somehow. And I'll talk about how bulk handles that problem later in the talk. So let's look at the current practice of how we allocate and use shared memory. So say I'm writing some function, F3, there on the right. So a lot of the times when we use shared memory on the GPU, it's so precious, right, that we have to use every drop of shared memory. We can't waste anything. So a lot of the times what we do is make this union of things that we know that we'll need later in the program. So say F3 is going to call two different functions, F1 and F2. They both require shared memory. So the nasty thing about this is that F3, function 3, it's actually responsible for allocating the resources that its callees are going to use, which is crazy. That's like in C, what if we had to allocate the stack frames that the functions that we were going to call we're going to use? That would be insane, but that's what we have to do today in CUDA. So we have to pass in F1 and F2's resources from the caller. So basically what this does is totally break encapsulation, right? Because the caller of F1 and F2 have to know all the details of how those two functions are implemented. It has to know all the details of the shared memory resources that it's going to need. And that just completely breaks encapsulation and makes things really difficult to compose. So productivity. Basically, I'm just going to argue that that bulk is a productive way to write code just by showing you lots of examples. I'm going to show you how we take groups of execution agents and reason about them, and I'll show you how to write things like Saxby, reductions, and finally a more sophisticated merge algorithm. So what's an execution agent? Well, an execution agent is a not necessarily thread. So it's kind of like a thread. It might correspond to a physical thread, but it's not necessarily a thread. So you can think of these as logical, lightweight threads, essentially CUDA threads. And each one of these agents has a parameter called grain size. So grain size you can think of as the quantum of sequential work. So basically, each execution agent sort of knows implicitly that it's a member of some larger computation. And within that larger computation, it has some assigned work it has to do, and that's sort of parameterized. The size of that work is parameterized by this number, grain size. And like CUDA threads, these guys are grouped into a tree structure, a hierarchy, and I'll show how that works a bit later. So let's take a look at what Saxby looks like. Let's just compile this code in our heads really quickly. So let's start at main. So I want to implement Saxby, so I need a couple of arrays, x and y. So those are just device vectors. But I want to basically launch this Saxby kernel, which is expressed as a C++ functor at the top of the screen there. So I know how much work I have to do. That's just n. So that's like in 1 to the 24th, or 2 to the 24th. That's something like 2 or 4 million, I guess. So I say bulk par of n, that big number. I pass an instance of this functor Saxby. So we can think of this struct Saxby as our global function, or our kernel. I pass this other special token, bulk root this exec. That's going to show us what I should stick into that first argument there in Saxby, that bulk agent variable named self. And then finally, I just pass the kernel parameters. So I say 13. 13 is just a number I picked out of my head, and then I pass 2 pointers to x and y to fit into those x and y parameters to Saxby. So to figure out, so when Saxby gets called, it's being called in parallel. It's being invoked in parallel by n of these execution agents. So I have to figure out what is the index of my agent. So I've got this little handle to the agent called self, and I say, well, the index is just self.index. It sort of knows. I can ask it which element this corresponds to. And then to implement the Saxby product, that's just a times x plus y. So that's our entire program to implement Saxby. And so this is just like writing CUDA code. But this bulk async call is going to smooth over a lot of the problems that CUDA would have otherwise presented for us. So let's take a look at exactly what bulk async is doing to us. The first thing we should notice is that there's no launch configuration, right? We didn't have to break our computation into thread blocks and threads, right? We just said we wanted n of these things. We don't care about how they're organized. There's basically no organization. It's just one big flat group of execution agents. So there's no launch configuration. There's no decomposition. We didn't have to marshal any of these parameters to async. We didn't have to marshal, the 2 pointers. If the parameters were very large, we wouldn't have to stage that in some strange way through global memory. This bulk async call is just going to do that for us. So basically, the goal here was just to make the easy stuff easy. So Saxby is, for some definition of easy, is fairly easy to write in this model. So how exactly does the automatic launch configuration work? So recall in the Saxby example, all we did was say bulk par of n to get our agents. We didn't have to say, well, we want the CUDA blocks to be 256, 512. We didn't have to figure out how many blocks we needed. We didn't have to think too much about occupancy. That's because what's going on under the covers is this occupancy promoting heuristic to choose the size of thread blocks. So when I say I want n different agents, the bulk async call is going to figure out how large those CUDA blocks need to be in order to give this kernel the best occupancy and promote the best performance. So basically, it picks the largest block size that's going to maximize this occupancy heuristic, and it's going to do that automatically. We don't have to worry about that sort of thing. So let's take a look at the signature of async. So if you're a C++ 11 programmer, this should look fairly similar. This is just a generalization of standard async, which is the asynchronous task launcher from C++ 11. The vanilla version of async just launches one individual task on some parallel thread. The way that bulk async works is by taking this extra parameter there at the front. It takes basically a description of a group of things or a group of tasks to launch, and everything else about the function is the same. It just returns a future that we can wait on to make sure that the kernel is done executing. So basically what this execution group parameter does is describe a tree. It basically describes how the execution agents are arranged and grouped into this hierarchy. And we saw in the async example, one of those parameters I passed was this bulk root, call it a cursor. Basically, that allows the async function to virtualize these execution agents and virtualize other things like shared memory, to sort of decouple it from machine resources. If you don't like that, you can just call it without that and just refer to thread index and block index, and that will just turn off all virtualization and make it look a lot more like writing a CUDA kernel. So, as I was saying, each of these execution agents are arranged into a group. And so in the first kind, there's two kinds of these groups. And the first one is parallel group. You can think of parallel group as a handle to the logical CUDA thread block. It's basically just an array of these agents. It knows things about its size. It knows how many agents are associated with the group. That size can be either dynamic or static. Static is sort of an important optimization. But you can see there on the second line, you can say things like bulk parallel group of agent and say, 128, give it a static size. So that's actually asking for 128 agents in a way that's statically and known at compile time. The second one of these groups is called the concurrent group, and this is just like the parallel group, except it adds a concurrency requirement. It basically gives a barrier to these groups. To synchronize, we see something like g.wait. And it basically allows the agents in this group to communicate and cooperate with each other. I can't really virtualize a concurrent group, so basically each concurrent group just corresponds one-to-one to a CUDA thread block. There's not really a good way to virtualize a group that's concurrent or has a barrier today in CUDA. That could change later, but for now, this corresponds one-to-one with a CTA. And I'll show you exactly how all this works with a few more examples. So let's take a look at how to write sum with this library. So we just want to sum up a bunch of numbers. So let's dive into main. We need an array of numbers. We'll just call that vec. That's just a device vector, and then somewhere to store the result. So we're going to sum up 512 ones, right? So the answer should be 512 when we're done. But let's take it the async line. So we're saying async of bulk : con of n. So what con of n means is that I need a concurrent group of n agents. So I need 512 CUDA threads, essentially. Then I'm going to pass the functor that we're going to call, which is sum. I'll show that later. This bulk root token is going to allow us to locate our group in the hierarchy once we get to the kernel. And then I just pass the data for the input and a place to store the result. So this is what the sum kernel looks like. It's C++, so it's just another one of these functors. The first argument I pass to the functor is this handle to the group, and that's just a concurrent group. We'll name that G. And then I've got device pointers that correspond to data and result. And so if I want to add up these numbers, all I do is call bulk reduce, right? So this is just like writing thrust code, except that I pass the bulk reduce call a handle to the group. So I'm passing it G as its first argument. And then the rest of the parameters are just like you'd see in thrust or the algorithms library. So I just say, I pass a couple of iterators, data, and then data plus the size of the group. That's just saying, here's the window of data that I want to sum over. I get the result, that's just S, the sum. And then I check my agent's index. If I'm the first index, or if I'm the first agent, I'll write the result. If I'm anyone else, I won't do anything. That's just, that's exactly how things work today in CUDA. If we're thread 0 in the thread block, we get all the crap work to do at the end. So agent 0 writes the result, and we're done. That's all we have to do to write a small reduction that could fit onto a single CUDA block. So let's take a look at the reduce signature. So this is basically a concurrent algorithm. So thrust gives us parallel algorithms. Boost gives us concurrent algorithms. So it gives us algorithms that could synchronize internally. So you can see the signature of reduce is exactly what you would find in thrust or the C++ 17 parallel algorithms library, except with the first parameter there is a handle to our group, concurrent group. Basically, when we call these concurrent algorithms, we're essentially, as a programmer, we're asserting that all of these different agents in this group token that I'm passing you, everyone is calling that algorithm concurrently. So we're all entering concurrently and then exiting concurrently. So there's an implicit barrier that happens before we return from this reduce. So the invocations synchronize, which makes it fairly easy to use these algorithms. So let's take a look at how reduce is implemented inside. So this is just library code that Bulk is providing to us. We don't have to write any of this. But it's the kind of thing that you would find if you were writing a CUDA reduction, except that the way we interact with shared memory is a lot nicer. So we've got this at the top here. You can see that we're actually mallocing. We're calling malloc within our reduction code concurrently. So you can see that we're calling to get a stage of shared memory that we can work in. We're calling bulk malloc. We're passing it again. That group parameter is the first argument to tell it that everyone in this group, every agent in this group, is calling malloc concurrently. They're all going to receive that same pointer S data to shared memory. And then we just copy from the input into the stage. That's just a call to copy in. And then the while loop there is just the typical while loop that you would see for implementing reduction. That's straight from CUDA. Except instead of calling sync threads, we're saying g.wait. That's the barrier. The entire group of agents synchronizes every time I call g.wait. And then when we're done with the loop, we do one more synchronize and free our shared memory stage, and then just return the result. So it's fairly easy to implement. You can see that this code looks a lot more maintainable than whatever is in Thrust today. And so in addition to reduce, we have an entire library of algorithms, the kind that you would see in Thrust. So things like accumulate, copy for each, sort, reduce by key. All these algorithms are there to be used concurrently within these bulk-style kernels. So the idea here is to provide a very nice kernel launcher in bulk async, and then once you're actually inside the kernel, to provide the same kind of standard algorithms you would get as first-class citizens of this bulk asynchronous world. So how does that malloc work? So we've actually got a heap running in each one of these concurrent groups that's serving segments out of shared memory. So that bulk async call is automatically setting up that heap for us based on, again, another one of these occupancy-based heuristics. It actually decides how much CUDA shared memory it needs to allocate at the kernel launch site for this to basically back this heap. We don't even have to specify that if we don't want to. Or if we do, we can actually explicitly request a heap size. But the nice thing about this heap is that it's backed by two different resources. So first, we're serving pages or serving segments out of on-chip memory, just CUDA shared memory. But what happens if we run out? We just start serving out from DRAM, right? So we just gracefully fall back to global memory. It gets slower, but it doesn't fall over, right? We can sort of rely on the code and use it robustly and sort of gracefully. It just makes it a lot more reliable and robust by having this virtualization that happens. So let's look at how the malloc can transform that code that we saw before. So recall before, to use CUDA shared memory, we actually had to allocate upfront statically how F1 and F2 were going to be able to use shared memory using the standard CUDA mechanisms, shared memory mechanisms. But if we just add in these malloc and free calls, F3 there on the right doesn't have to know anything about what F1 and F2 are up to. It just has to pass that handle to the group so that F1 and F2 are able to allocate and synchronize inside. But it doesn't need to know how many resources those two child functions actually require. It just makes this code a lot easier to maintain, and basically we don't have to worry about if these resources are going to run out. So let's look at some more interesting kernels. So before I showed you how to reduce or sum up a single small group of numbers, but say we had lots and lots of different intervals that we wanted to sum up. So this is basically a segmented reduction. So let's dive into the code here in main. Say we want to sum up 4 intervals. So we say num intervals 4, and each one of these intervals is sized 256. So we need a couple of pieces of data, input and sums. Those are just device vectors. We're going to sum up the numbers in the input array. And for each of those intervals, we're going to store it in this sums array. And then to do this, we just call bulk async. But this time, instead of saying bulk par or bulk con, we actually nest these calls together. So we're actually creating a hierarchy of these groups. So they're at the outermost layer. We're saying we want a parallel group of concurrent groups of agents. So this is a sort of a two or three level hierarchy, depending on how you count. But anyway, this corresponds to a CUDA thread or a CUDA grid. We've got lots of groups that can synchronize, and each one of them can synchronize, and we've got lots of them going in parallel. And then we just pass the rest of the arguments to the kernel. And this is what the kernel looks like. So the first parameter is sort of describing the hierarchy of these groups. So this is a parallel group of concurrent groups. So it's a two-level hierarchy, and then we just have our parameters that describe how the data is laid out. And so to sum up each of these intervals of numbers, we sort of get the index to the current group. We find where the interval lives in the input. And then, again, we just call bulk reduce to sum up that interval of numbers corresponding to our current group. And then, if we're the first agent in the group, we just store the sum to memory. And each group does that. So this is basically a generalization of the sum kernel. We're just doing lots of different sums in parallel. And I guess I just wanted to point out in this call, before we said par of con, we sort of nested these two execution policies together. The shorthand for that is just grid. So this is just like a CUDA grid. So we have num intervals, essentially CUDA blocks, and then each one of these blocks has some size. So that's it's basically a one-to-one mapping between this bulk style of describing the computation and CUDA. So as I was saying, these execution hierarchies sort of nest together recursively. So you can sort of describe arbitrary hierarchies. So the way you would describe something that corresponds to CUDA would be to say parallel group of concurrent group of agents. So that's you can think of each agent as a CUDA thread, each concurrent group as a CUDA thread block, and then the highest parallel group, that's just a CUDA grid. And even though you can sort of put these things together arbitrarily, only a few of these nestings actually sort of make sense to execute on hardware. So only a few of these different kinds of nestings are implemented. And you can sort of traverse down the hierarchy to find the index of your agent or your grid using this syntax at the bottom here. So the last example I want to talk about is a merge algorithm. So this basically if you saw Sean Baxter's talk yesterday, I think he was talking about the merge path algorithm. I want to talk about how to implement it with bulk. So basically, we're going to be merging two sorted lists into a single sorted list. So we've got sorted lists A and B there at the top. So to implement this, we're going to chop up A and B into these different tiles. You can see they're sort of colored differently. We're going to take each of these pairs of tiles from A and B, move them into a stage where we can compute and sort these things cooperatively or concurrently, and basically merge them within this stage. And then when we're done, we're just going to store it back out to this sorted list C. So C will be the merger of A and B. So this is really easy to implement with bulk. So let's take a look at how merge looks. So this is implementing the merge path algorithm. It's not really important to understand what merge path is or how it works. But down here at this thrust tabulate call, you can basically think of this locate merge path function as an oracle that it's going to tell us where to start reading in the async call below. So it's not important to understand how that works. But what I want to show you is exactly how this step where we merge each one of these partitions, each one of these shaded partitions, A and B, works in the stage. So we're going to say bulk async. We're going to launch a grid, essentially. And because we want it to run fast, we've chosen the group size and the grain size statically. They're at the bottom there. So instead of passing variables, these are actually template parameters. It just allows us to run faster. We could have done it dynamically, but if we do it statically, we can go a lot faster, especially on Kepler. So you can think of this as just launching a CUDA grid. We instantiate a merge kernel there. The second argument, we pass another one of these tokens to locate ourselves in the hierarchy, and then we pass the parameters there at the bottom. So let's take a look at what the merge kernel looks like. So most of this code is actually doing just index bookkeeping to find to locate the data, the input data, and that's not really that interesting to us. It just happens to take up most of the code. But dive down to the bottom there, you can see that in order to do this staging part, where we bring each of these tiles into a shared memory stage and then merge, that's implemented by just mallocing an allocation, place to keep the stage. There we just use a bulk malloc to allocate the stage. And then we call this staged merge function, I'll talk about on the next slide. And we basically pass pointers to the two tiles in the input so that they can be merged within shared memory. And then finally we free the shared memory stage there at the bottom. So let's take a look at how staged merge is implemented. So again, we pass this first parameter, which is describing how the group is set up. So basically, we've got a single concurrent group of agents, and we know both the sort of agent grain size and the group size, the size of the concurrent group statically. That's why those are template parameters. And then we just have pointers to the data. We have a pointer to A. We have the size of A in 1, a pointer to B, the size of B in 2. We have a pointer to the stage, and then we have a pointer to where the merged result will live in the output. And it's basically just implementing the slide I showed you visually before. The first thing we do is just copy data into the stage. That looks exactly like using a standard algorithm. The sort of wrinkle here is that we've made a fancy kind of iterator to join A and B together as we copy. We could have copied each of A and B separately. It's a little bit slower if we don't do that, so that's why I added the join iterator that lets us copy with a single call. Then we could just call Inplace Merge once the data is in the stage. That's just going to merge the data in place. There's nothing weird going on here. And then finally, once the data is merged in the stage, we just copy to the result. And that's that call to copy in. We're just taking a pointer to the stage. We're saying, okay, the size of data in the stage is the sum of the two input sizes, and then we start storing to the output, which is at C. So it's the bog standard call to copy in. The sort of strange thing I want to point out is that we've sort of taken the handle to the group, and we've sort of bounded the amount of work that it's going to do statically. That's what these calls to bound are doing. The reason to do this is to basically let the compiler know statically how much work each of these calls is going to do, which is going to allow the compiler to basically inline the loops and keep variables within registers. It's sort of an ugliness that's required to get really good performance. Basically, this call to bulk bound basically provides an upper bound on the size of work an algorithm is going to do, and it's sort of as I was saying, it allows us to inline these loops because we know they're bound. We know the number of iterations they're going to perform. And it allows us to keep results within registers. Otherwise, it would fall back to a local memory and basically get a lot slower. So this is what Inplace Merge looks like inside. So Inplace Merge is just a library call that we're calling to bulk. We didn't have to implement this. But I just want to point out how readable it is if you look at the body. I admit the signature is a mess, full of C++ nonsense, but it's allowing us to get good performance. So the way that Inplace Merge works is to first call this merge path algorithm, this sort of oracle that's going to tell us where to start reading in the input to merge our data. And then each one of these execution agents is going to create a local result, and that's going to go in this local array, local result, which is sized with this grain size parameter. And then each one of these agents is just going to call merge. So it's really easy to reason about, right? We're just finding where to read in the input. Everyone does a merge. We do a barrier at g.wait. and then we just copy back to the output there at the end with the copy in result, and then synchronize at the end. And if you were to see that the code that this is replacing, the old code in Thrust that was completely unreasonable, completely unreadable, and completely unmaintainable, that code would consume the rest of my talk to be able to talk about that code. Thousands of lines neatly, we can neatly substitute here with just a few lines of code that is very maintainable. So there's even more examples on GitHub. There's that hello world. There's an async reduce example. So I'm always getting questions how to do a reduction asynchronously in Thrust. So the way that Thrust reduce works is that it does a reduction and then it copies back to the result, and people hate that, right? You can actually make it work asynchronously if you use bulk and basically follow the steps in that example. I didn't talk about it today, but the way that all of these bulk async calls work is by returning a C++ style future. So you can get concurrent execution of these functions. There's an example, a futures example about that. There's the merge example. There's a sort example, a larger example. I didn't have time to talk about it today, but it's there. Just a lot of different examples of implementing Thrust style algorithms with this interface. So as I was saying, you can get really productive and write really lean code. So if we look at the lines of code that this is replacing in Thrust, they're on the left. So just to write for each before I had this library, it required 200 lines of code, right? That's completely unreasonable. For each is like the simplest algorithm in the world. If we use bulk, we can do it in 10 lines of code. The old Thrust reduce was like 300 or so lines of code. We can implement it in a robust manner using bulk in 85 lines or so. Inclusive scan, like the old scan code in Thrust, was absolutely horrible. 750 lines, we can get by with only 130 using bulk. The merge code is probably half the size. Reduce by key is probably around a third to a fourth of the size now. So we started out as old fat Arnold. Now we're the younger, leaner, bulkier Arnold. After replacing, substituting new implementations. So you're probably asking, okay, fine, but what about the performance? Well, I'm happy to tell you that we can basically match the performance that you would find in Sean Baxter's modern GPU library. So if we take a look at reduce, we can look at 3 different implementations of the reduce algorithm. One is the top, the blue line is something I've written similar to what you saw in the slides before using bulk. The red line is Sean Baxter's code, which I'm basically taking as a benchmark for high performance code. And then finally, the orange line is the old Thrust code that's been replaced. And you can see that we can basically match Sean's code there with the blue and red lines, and get you can actually get a much nicer looking code, and you actually get much nicer performance. So that's the 32-bit floating point reduction performance. You can see that again we're matching for the 64-bit case. Scan is an even better story. So you can't even see them because all 3 of these lines are basically the same up there at the top. So I've timed 2 different implementations of prefix sum using bulk. One is where I've explicitly chosen a size for the shared heap that I talked about before. The other is where I let the system choose the size of the shared heap itself. And you can see that there's basically no difference for this particular algorithm between those 2 different implementations and Sean Baxter's modern GPU implementation. And this is replacing, this is almost 2 times the performance of the old crappy scan, unmaintainable scan from Thrust. So I'm very happy about that. That's for the 32-bit integer case. If we can take a look at merge, you can see that the rock is getting a little bit concerned over the performance here of the bulk code. You can see that if we don't use a heap at all, there on the left, that the bulk implementation is on par with Sean's modern GPU implementation. If we introduce the heap, basically allocate our shared memory with malloc, you can see that we pay a little bit of performance for that. Those are the yellow and green lines that are essentially on top of each other in that left graph there. But you can see that Even though it's a little bit slower than Sean's implementation, it's twice the speed of the old crappy thrust implementation. And it's basically the same story for floating point merge there on the right. But we can make the rock happy if we show him the reduce by key benchmarks. Sean, at the time I put together these slides, Sean didn't have an implementation of reduce by key, so I'm not comparing our segmented reduction implementation to his, just thrust here. But you can see it's like about 50% faster there than the orange line, the old reduce by key and thrust, if we replace it with these better implementations built with bulk here. So I guess the point I'm getting is we don't actually lose too much performance by targeting a higher level of abstraction and writing code in a much more maintainable way. So I hope if there's any takeaway that you take away from this talk, I hope it's this takeaway. So this basically wraps it up. I want to point out this library is a work in progress. My first priority in future work is to make all of these examples much simpler and faster. So the interface will probably change. Once the interface we feel it's good and can probably be maintained and stable, we might actually expose it in thrust so everyone can use it and without having to go find a separate library. None of what I've talked about today runs on CPUs, but that's an important goal. We shouldn't have to write code in weird ways depending on the processor that we're targeting. So I'd like to find a way to target CPUs with this library and even distributed environments of CPUs and GPUs. Because the ultimate goal is basically to write once, run everywhere, right? That's sort of been the promise that we've seen from a lot of different programming models. I don't think anyone has really delivered it yet, but that's basically what I want to drive towards. And that basically wraps it up. All this stuff is on GitHub. You can find bulk there. If you're not really that interested in bulk and just wanted to take a look at the shared malloc implementation, that's there as a standalone implementation that you can just drop into your CUDA codes immediately and start using a shared memory heap. And with that, I guess yield the rest of the time to questions.